On today's session. This session is going to be conducted in two parts. Training session 1, networking, in which we are going to cover networking fundamentals plus some extended topics. In training session 2, we are going to cover browser rendering and navigation timing API. So keep watching with us. So before jumping into the session, I would like to talk about PUBG. So PUBG without a U, PBG. The purpose, benefit and goal of going through this entire session. The purpose of today's session is to understand how communication happens on the internet and how data passing happens through the browser to user readable and responsive formats. Next, the benefit of having this knowledge. We can improve website performance, optimize network requests, increase visibility and monitoring of performance, and much more, mainly achieving the cost efficiency. So the overall goal is to deliver user experience and maximizing business outcomes. So let's jump into the session now. So the first topic here is about the networking fundamentals. So talking more about networking fundamentals, starting with the definition, a basic standard definition of networking fundamentals. Collection of interconnected devices that can communicate with each other to share resources, data and information. So this is a very basic definition which itself explains, where in the image also you can see it's a collection of a lot of people who are trying to share some sort of data, resources and information among themselves. So how that is achieved? We will need some kind of medium for that. And there are only two ways. One is wired and one is wireless. So any of these will be considered as a network. Collection of interconnected devices that can communicate with each other to share resources, data and information. So explaining it with an example, two people doing chat on the WhatsApp are connected in a network. Only then from one device to the other device, one person can send a message and the other person can receive a message. So in the networking fundamentals, we are going to cover first of all the reference model, TCP/IP and HTTP. Then is SSL, the importance of security. Then the trace route paying certain commands. Talking on BGP, the Border Gateway Protocol, DNS, CDNs. So we are going to try to cover these topics in our coming slides. So let's move forward. So first we are going to start with TCP/IP model. TCP/IP model here is which is a kind of reference model used to better understand the flow of traffic in a particular network. So taking an example here, on the screen we have sending host, receiving host. So sending host starts sending the request to the server. So here sending host is a client and receiving host is a server. So from client we are sending a request to the server for a login. So how that is going to travel on the client's machine, which will be named as sending host, and how it is going to be interpreted by the server on the receiving host side. So from the client side, first of all, the application layer will come into picture, where the user is interacting directly with the user interface or operating system on the machine. And from the application, the client initiates a login request, which is further encapsulated into the transport layer with the TCP segment, further internet layer in the IP datagram. Then in the data link layer, the frame, header and tail is added. On the physical layer, it's finally converted into bits, ones and zeros, which can travel on a network. and it is forwarded towards the receiving host. Now, receiving host on the physical network layer is going to receive the ones and zeros in a similar manner, and then it's going to start the decapsulation process up in the hierarchy. On the data link layer, it's going to start detaching the frame, and all these layers are going to give us some different specific values or the IPs or the port or the MAC addresses. So every layer has its own purpose here. So moving forward from the data link layer up in the hierarchy, internet layer, which is going to return the IP, from which source IP this request is coming from, then the transport layer, TCP segment, and finally the application layer, where the server will be able to know what exactly the request is, and the server will know this is a login request. So now, in this entire process, where is the performance coming into picture? So how we can connect performance with this? In order to understand that, let's move forward, compare the TCP IP and OSI model. So OSI is an older model as a reference model which was used. These days, TCP IP is being used in most of the places. So they are quite similar. Application layer is a combination of 3 layers which were used to be referenced in the OSI model: application layer, presentation layer, and session layer. Similarly, we can see the transport layer in OSI and TCP are quite similar. OSI's network layer was renamed as internet layer, and OSI model have 2 other layer: data link layer, physical layer, which was merged into the link layer. Now all these layers are going to have different kind of protocols, and that is the place where performance actually comes into picture. So in this, where the protocols are coming into picture, this is the place that actually adds the performance or impacts the performance here. So DNS, for taking an example, at application layer, the DNS, how much time DNS is taking to resolve, and then at different level like transport layer, TCP, UDP, how much time the TCP is going to take in order to make a reliable connection between client and server before the first packet can be sent on the wire. So all these protocols are going to impact our performance. So we are going to study these protocols in much more detail. And we are also going to cover how we can troubleshoot certain things like reachability and availability in the upcoming slides. And giving you a kind of definition around the protocols. Protocols at each layer of the network stack. So we are considering this reference model as a network stack, play a crucial role. So these are going to play a crucial role in determining the performance of websites or the web applications which we are running on the operating system through the browsers. So let's start with the transmission control protocol, which is the TCP protocol used on the transport layer. Now the key performance metrics in this are going to be round trip time, which is RTT, which is going to measure the time it takes for a signal to travel from the source to the destination and back. We are going to also see the use case of RTT in upcoming commands like ping or even the trace route command, in which how the probing is working. So the RTT is very important here. The next one is packet loss. And just to conclude around the RTT, lower the RTT, it's going to indicate faster the communication is going to happen. So RTT should be small. Next is packet loss. The percentage of packets that are sent but not received are called as a packet loss. It's called as a packet loss, and we can observe this in the Wireshark packet capture. So in this case, lower the packet loss is going to indicate more reliable connection. So everyone wants the packet should not be getting lost. It's going to add more latency or retransmissions. So talking next about the retransmission, the number of packets that need to be resent due to error or loss. Here loss is we are referencing to packet loss. So fewer retransmission are going to indicate a more stable connection. So we want to avoid retransmissions as much as possible. That is why we are working with the TCP, which is more reliable. It's going to make sure that the waiting for an acknowledgement from the server side, but it's not a case where retransmissions will not happen, but at least the client will know there is something going wrong in the path where the communication is trying to happen. The next is congestion window. The amount of data the sender is allowed to send before waiting for an acknowledgement is known as the congestion window. So how much we can wait. So a larger congestion window is going to give us better network conditions. So if there is less congestion on the network, it is always better. The next is the receiving window. So the name itself explains how much data we can receive without getting overwhelmed. So a larger receiving window here is going to indicate that the receiver can handle more data, which is going to again help or increase the buffer size and is going to help us in the smooth communication. And at the end, it's going to help us improve the performance as well. So talking about some of the tools which we can use. So the first tool is ping. So ping command is a very strong tool which we can use from the terminal on the macOS, and on the Windows we can use the command prompt in order to run the ping. Ping works on, by default it works on the ICMP protocol, but we can also configure it in order to use TCP and UDP as well. So ping can support up to 3 protocols: ICMP, TCP and UDP. And it is going to help us test the reachability of a host on an IP network to measure the round trip time. So we initially also discussed about what is round trip time, and this is the command which we can use in order to calculate the round trip time. And round trip time for the messages sent from the host to the destination host. So there is a source host towards the destination host. So ping with TCP or UDP can calculate the round trip time, but not the port reachability. If we say on the TCP and UDP we can check the availability of a port, that is not possible with the use of ping command. And we can have some other tool which we can use and have a discussion in order to check the availability of the port. But for ping, it's solely the purpose is to check the reachability. And the kind of working we have is running a ping test from hop by hop, like from one location to the another destination. It's going to travel hop by hop. And we are going to send on average 5 pings, which normally how the ping works, and it's going to wait for an acknowledgement, how quickly the response is coming back, and it's going to tell us if there is any kind of packet loss happening. So further, in order to compare, I have added a table here in order to better see the difference between ping, ICMP, TCP and UDP. And we can see the protocols are different which are being used. Use case is also different. So ICMP is mostly observed to be blocked due to firewall blocks. Normally ICMP probes are not allowed. If in special case we are raising a request and explicitly asking to transport layer security. So how the TLS impacts the performance and what exactly happens in the TLS. So giving an overview of TLS, after the TCP handshake, there will be a TLS negotiation happening in the client hello and the server hello, where the certificate exchange would happen and a session key will be created and a symmetric encryption will be used. So in this, how the performance we can evaluate the TLS certificate overhead. So while the certificates are getting exchanged and we are accessing a particular website, so let's try to understand it better with the example. So first impact is having a overhead of the subject alternate name, where a single certificate is being used for a lot many websites. So a SAN is going to have a lot of certificates in it. So that is one of the point, but normally SAN certificates do not inherently add significant overhead during the SSL handshake compared to single domain certificates. But the only difference here would be the size. The additional SAN entries are going to slightly increase the handshake time. The next is like the managing efficiency. So reducing the need for multiple certificates, simplifying management, and potentially improving overall system performance by reducing the complexity of the SSL configuration is the goal here. So the next is session resumption. So session resumption is how quickly a client accessing a particular session can resume back into it. So there is a more possibility of a user accessing the same website would come back in after some time in order to access it again. So that is done with the help of session ID and session token tickets. Yeah, it's ticket. So session ID, the server and client use a session ID to resume a previous session, reducing the need for a full handshake. Whereas session ticket, it's more efficient mechanism. In session IDs, the server provides the client with an encrypted session ticket, and that the client is going to use in order to resume the session. Yeah. So further we have HTTP 2 and HTTP 3, in which both of these are going to require the TLS, and we can have a broader level difference between HTTP 2 and the generations of HTTP. So HTTP is a application layer protocol used for transmitting hypermedia documents over the internet. It works on client server architecture, and it is a stateless protocol. Each request from a client to a server is treated independently. That is what stateless means, without any knowledge of the previous request. So the next requests which are going to be forwarded towards the server are not having any knowledge of the previous request. So that way it is going to be an independent way of communication, which is going to have its own challenges as well. So in order to cover those challenges, there were certain techniques being used, like caching the session states or using the session tokens and cookies. So that is how we normally, in today's world as well, we use cookies and session token to learn more about the user and keep the status recorded for the for that particular client session. So this is how over the period of time HTTP have grown. In HTTP 1 there was no keep alive, so which was adding a lot of latency, because for each and every new GET request, HTTP request, there was a requirement of having a new TCP handshake at each level. Whereas in HTTP 1.1, which was able to overcome that with the use of keep alive, so we can keep a TCP handshake, TCP session alive, and keep on sending multiple HTTP requests in the same TCP session till the keep alive is able to keep the session alive for that TCP. And it also came up with the pipelining concept. So pipelining helped in this by pipelining. We can understand it better in terms of, like, we can continuously keep on sending the information from the client side before waiting for the first acknowledgement from the server side. So multiple requests can be sent without even waiting for the acknowledgement, and later on server can acknowledge those multiple requests which were sent. So that is the concept of pipeline. Then in the HTTP2, the TCP streams plus push capability came up. So TCP streams is something in which each and individually the TCP requests, TCP handshakes were different. So in HTTP 1.1 we have a drawback of headline block. So headline block means if one request is blocked, all the rest of the request coming behind that in the same TCP handshake will also keep on waiting for the first request to get a response or why it was dropped. Until and unless it is resumed, everything is stuck behind that. But in this, TCP streams are independent, so it was in HTTP2 we were able to resolve the transport layer problem of headline block. And it also came up with push capability. So push capability helps in order to, if required, if there is some HTTP request which needs to be pushed forward immediately, we can prioritize that, and we can push that as soon as possible towards the server with the help of certain flags. In HTTP3 we used UDP streams. So here instead of TCP, UDP protocol was used, which was much more faster. In faster, we can say it's not reliable because it's going to keep on sending the information from the client side before waiting for any kind of acknowledgement, and it works on a timeout mechanism. The time period that it is defined is going to forward the traffic, and in order to make it more reliable, we started the use of connection IDs along with it. So in HTTP3 we were able to solve the problem of headline block, not only on the transport layer but also at the application layer as well. So this was the overall growth of HTTP over the period of time. Yeah. So moving on to the next is HTTP header, how HTTP header looks like. HTTP header is going to comprise of three different headers: general, request header, response header. So I will be going through this on a broader level, and you can also navigate to any of this on your developers tool on the browser and have a look at any particular page. So in this I have referred the cnn.com page. In the request URL, request method, it is a get request which is sent when we want to fetch some information. Then status code is 301 moved permanently, which means there was a redirection captured by the client and it was redirected towards some different website, which we are going to see later in the response header, which URL we need to refer. Remote address, this is an address of the server from where we are getting a response from 443 port. Referrer policy, so strict origin, when cross origin, this is a security policy used when there is a domain change or a cross origin request initiated. Then accept ranges, so coming to the response header, accept ranges, the data which client can receive back is in the form of bytes. Alt services is going to give the information about the header information. So header 3 on port 443, maximum age is this, header 3 version this. So these are all the supported headers and their version with the maximum age. Then is cache control. Cache control is going to this set the directives. So cache control directives is going to tell public message. So public means it can be cached at any place. It can be cached on the browser, in the intermediate proxy, and on the router's cache as well. Maximum age, for how long we can cache that information until it gets stale. The next is content length, date, at what time, location. So this is very important. Location field in the response header only comes up when there is a status code of 301 which says moved permanently. So which website we need to now refer further in the redirection, that is www.cnn.com. Now the retry after 0, the server responding this request is hosted in Varnish. So set cookie, so these are the cookie information which we have. Then is via which version of that server we have received the response. So cookie information is specifically in order to know the user better, we are storing that cookies information, so that next time the user will come back to access the server would know what information we need to show to the user might be interested in. Then is the cache information. So X cache, it's going to tell us whether it was a CDN which was which had a hit in order to deliver this information, and this information was not actually delivered from the server, but a CDN sitting in between. And which, so X served by tells which node was able to serve that request. Then there is a request header authority which says cnn.com. This all things were requested by the client. Method is get again. Path, this is a home directory. Schema used was an HTTPS, which was a secured way. Except, so these are the like negotiation details which client is sending, that this is acceptable format which I can accept from the server, except encoding, what encoding it supports, except language, priority, how at what priority we need to get a response for this. Then there are the sec entries, which is again a security field which is added by the browser which is forwarding this request to the server. Then there is upgrade and secure request, which is set to 1, which would mean this is a secured request set with the help of HTTPS, which is a TLS encryption connection. And then is the user agent, and user agent is also very important. What user agent is forwarding this request, it's going to tell us about the browser information. So yeah, that was. And the very important, which is the HTTP status code. So these are considered to be the first line response header, which indicates results of request in 5 groups. First is the 100 range, which is informational. 200 range is successful. 300 range is client is redirected to different resource, and that is going to be the 300 range. 400 is going to be request contains an error, and 500 is server encountered an error fulfilling the request. So any error from the server side is 500, and any error on the client side is 400.